experience with our participants. Really, it's very much useful for us.
Thank you for inviting me. Thank you for inviting me. Thank you very much.
Yeah. I'm also very happy to see you through online.
Hopefully, one time we'll see each other in person. Another one of my former colleagues from the bar group, Ashish Kumar Satpathy, invited me to. You guys have a meeting of the Indian Electrochemical Society, I think.
Yeah, okay.
And he invited me last year, but I became
This meeting is being recorded.
And so I couldn't go because of my baby girl. So maybe after the pandemic, there will be a chance and I can meet you all in person.
Family.
I will love to.
Yeah, please come.
Thank you for having me.
So thank you, Dr. Hicks Aurora. I think it's a midnight in the United States, so you were banning your sleeping time in the for our Indians and residents. I think now it's around midnight, around 12, more than 12. Yeah. Okay, you are traveling the next day, so yeah, okay. So thank you very much for electrochemistry. I think all the participants enjoyed your talk, and it's reflected from the questions, participants, and everything. So I would like to extend my thanks on behalf of the organizing committee, on behalf of me, for giving to our sharing your valuable time in this international conference. Thank you, Araya. Thank you very much.
Thank you, sir. Am I audible to you, sir?
You're audible.
Yeah, fine, sir. We people are really fortunate to have you, sir, with us today. Undoubtedly, it's a terrific delivery for the past 1 hour with your wonderful results. Hope it will be more useful to the participants. We heartily thank once again on behalf of the organizing committee. Thank you so much, Professor Nets Arroyo, sir. We are happy to see you in India soon, sir. Thank you so much.
Thank you. Keep enjoying the conference. I'm gonna go to bed.
And
thank you, everyone.
Personally, I would like to thank sir. You just reply even in the midnight, and we really fortunate. And I have to thank once again, sir. Thank you so much. Yes, sir. Okay, by this time, I would like to register my sincere thanks to our beloved professor, Dr. P. Suresh, sir, for accepting this kind request, and you lead this past 1 hour in a very active manner, sir. Thank you so much on behalf of the ETOTS 2022, sir. Thank you so much.
Thank you for this opportunity.
Thank you, sir.
Thank you very much.
Yeah, thank you so much. Without further delay, let me move on to the technical session 1, invited lecture 2. For this session, now I would like to invite Dr. J. Anaraj, sir, Head and Assistant Professor, Department of Material Science, School of Chemistry, Madurai Kamaraj University, to chair this session by Dr. S. Sendil Kumar, sir, Principal Scientist, CSIR, Sikri, Karaikudi, Tamil Nadu, India. So now I hand over the session to Dr. Anaraj, sir. Please.
Thank you, Dr. L. Raja. And I thank Professor V.S. Vasanta for giving me this opportunity. It is my great pleasure and to introduce Dr. S. Sandil Kumar, Principal Scientist, Electrotechs and Electrocatalysis Division, Central Electrochemical Research Institute, Karaikudi. Professor has done his master's degree in the Sri Ramakrishna Vidyalaya College, Coimbatore, in the year 2002. PhD, he has pursued his PhD in the year 2008 with Sikri and Bharat University, Trichy. Professor has several professional appointments as he has research postdoctoral fellow at Arizona University, Tampa, USA, junior scientist at CSIR Sikri, scientist at CSIR Sikri, Karaikudi in the year 2015, senior scientist at Sikri in the year 2019, and as now currently is pursuing his academic career as a principal scientist, CSIR Sikri, Karaikudi in the year 2019 onwards. Professor is very much interested in the research of the development of nanomaterials in electrochemistry, selective electrocatalysis based on noble and non-noble metal nanoparticles for enhancing the energy efficiency of electrochemical reactions like methanol oxidation, hydrogen evaporation reaction, oxidation reduction reaction, luminophores, and co-reactants for fundamentals of biosensors and their applications.
Mask proper.
Professor has awarded Boy Scout Fellowship in his credit from DST in New Delhi for conducting advanced research in the area of chemical aspects of nanomaterials and nanotechnology in the University of Texas at Austin, USA in the year 2012. Visiting professor with the Alan Bond at Monash University, Melbourne, Australia. Visiting scientist in Nanoix Imaging Limited, High-Tech Park, Jerusalem, USA, Israel in the year 2016. And worked as a visiting scientist and professor at Professor Fitz University of Greifswald, Germany in the year 2017. India DAD collaborative project. Also, professor has carried out 9 projects. Among them, some of them are ongoing projects with a cumulative amount of more than 2 crores. Apart from these projects, he has completed 4 CSIR major projects with a cumulative amount of 80 crores. And he has published more than 50 well-reputed journals in his credit. So with this introduction, I call upon Professor Sendil Kumar to deliver his lecture on electro-generated chemiluminescence, fundamentals and its potential applications versus bioanalysis. Call upon Professor Sendil Kumar. Dr. Sendil Kumar.
Thank you, Professor Annarat sir, for your kind introduction. First of all, I thank organizer, especially Vasudha madam, who involved me in this program actively and share my research experience with you all in this forum. So even though we are all working on electrocatalysis, okay, modified electrodes, okay, but we are specifically working on this kind of unique field called electro-generated chemiluminescence. Okay, so this is like a unique field. In India, maybe a few groups, maybe 1 or 2 groups are working. Why I am saying, because there is no commercial instrument, so we have to inbuild our own and study the intrinsic properties of some particular materials and its applications to that particular, especially some biosensor applications. So you all aware that this is my institute main building. I am from, as Anarath sir said, we are from. I am from Central Electrochemical Research Institute. Basically, most of the electroanalytical based in India. It is one of the pioneer institute where we are working about batteries, sensors, and coating technology, corrosion technology, so many things. Okay. So today I am going to share some of my research work with the electrochemiluminescence based work. So before going to my topic, I have to introduce what kind of why this luminescence. Okay, what kind of luminescence are there? How they are generating. Okay, why need how? What are all the types in that luminescence? So if you look at the simple definition of luminescence, is a simple light emission process when the molecule falls from excited to the ground state. So this is the luminescence definition. Okay, when you are interacting the 2 molecules, one molecule goes to excited state, then ultimately it comes to the ground state. While that time it decays the lights. Okay, this is like a simple definition. But how it happens? How this one molecule will go to the excited states. So based on the triggers like chemicals, lights, organisms, you can name it that particular luminescence. Okay, for example, if you use chemiluminescence, you have to use some chemicals. Okay, so that chemicals interacts each other and goes to the excited state. Similarly, you are taking one chemical, but if you are using a light source to excite that molecule, then it is called photoluminescence. Similarly, biomolecules, so the organisms, when you are using an organism to stimulate that particular molecule to the excited state means called bioluminescence. And radioluminescence or radiochemiluminescence means you are using a radiation. Radiation waves means high frequency radiations, gamma ray radiations kind of things you have to use for exciting that particular molecule to decay the light. Okay. Similarly, sonic waves, ultrasonic waves are high frequency range. Okay, that also people are utilizing to generate the luminescence. So that process is called sonoluminescence. So among these things, electrochemiluminescence are very special because you can use some potential or current. Okay, electrochemistry means mainly whether you have to use either potential or current one. Okay, so when you use some electrochemical energy in terms of current or potential, then one can able to promote one molecule from ground state to excited state and ultimately decays the lights. So this is called electrochemiluminescence. This is what maybe another couple of 30 minutes we are going to discuss. Okay, so maybe I can recall our previous speaker, one of my friend, Nuts, mentioning that square wave voltammetry. Okay, so why he is using that square wave voltammetry, or why he need that development of that software? Because it needs to, or it improves the sensitivity. Okay, because otherwise in general cyclic voltammetry or linear sweep voltammetry, it always has some background signals, which ultimately this electrochemiluminescence has some merits. Okay, instead of just you can use like you don't need to worry about this background current. That is the greatest advantage. So the electrochemiluminescence is nothing but by coupling two techniques like electrochemistry and spectroscopy. So we are coupling these two. People will say like marriage between electrochemistry and spectroscopy, it is called like electrochemiluminescence. Okay, so if you look at the exact definition, ECL, it is simply called ECL. It involves generation of species at the electrode-electrolyte interface that undergo electron transfer reaction from an excited state, okay, to form an excited state, which decay of the light emission without involving any external light source. Okay, so hopefully you understand the definition. Okay, this ECL, that light emissions occurs at the electrode-electrolyte interface where that energetic electron transfer takes place. Okay, so during the energetic electron transfer, that molecule will go to the excited state and ultimately decay the light without involving any external light source. Okay, that is the main difference between photoluminescence and electrochemiluminescence. I am showing you some schematic diagram of 3+. Similarly, another molecule will also oxidize like a tripropylamine. Okay, so that tripropylamine oxidize and produce intermediates like tripropyl cationic radical. So TPA dot plus. Okay, this tripropylamine cation radical interact with the oxidation form of ruthenium 2+. Okay, so these are all the happens. These are all the electrochemical reactions happens at the electrode interface. That is where I am showing electrochemiluminescence or electro-generated. So these intermediates generated at the interface, then these two, the generated intermediates interacting together and emit the lights. It is called chemiluminescence. Okay, so the triggering point going to be like in terms of current or potential, you are generating the intermediates and ultimately you are able to see the light emission on the electrode surface. So this is the simple definition and schematic diagram, but I am going to tell you some detailed why we need this kind of luminophores or TPRA. That is the real fundamental issues that we are going to see now. My subsequent slides for another 10 to 15 minutes, and ultimately we are going to see some specific applications. So this is the merits, or if you look at the history, that ECL phenomena was observed during electrolysis in the late of 1920, but the first detailed ECL study was reported by Hercules and Bard in 1960. Okay, so these two groups tremendously putting their efforts to understand the fundamentals and improving the electrochemiluminescence light emissions. Okay, So the merit of ECL, that's what I told. The merit of the ECL is very high sensitivity. There is no background current and good temporal and high spatial resolution. And it is like a simple, simplified optical setup. It doesn't involve any complicated instruments or sophisticated instruments. So you can inbuild your own with some small optics. Okay. So that is the greatest advantage in the cost point of view. And it has some good temporal, because if you the complementary technique going to be like a fluorescence technique. Fluorescence techniques also it is like optical technique, but you see always this scattered lights or background signals are very high, which limits the sensitivity. But here the light emission is triggered by the potential, which ultimately improves the high sensitivity, and it is independent of that surface. It is like even you can use a bulk electrode instead of microelectrode or to reduce the background current. Okay, you can able to see the nanomolar or picomolar sensitivity. And when you go for some imaging or signal to noise ratio, it has some good spatial temporal resolutions. Okay, so that is the greatest advantage. Moreover, this kind of techniques, this kind of unique technique, ECL can also coupled with electrophoresis or high liquid HPLC or flow injection analysis to improve further or a real samples advantage when you go for this kind of ECL based sensors. Okay. So now I am going to talk about some fundamentals, how this light emissions occurs. Okay, for that you have to see the reaction mechanism at the interface. In general, any ECL reaction, if you take, two reactions mechanism is adopted. Okay, one is ECL, the dotted line you can see here, like ECL response, the continuous line is showing the typical CV response. So you can see here almost 1.1 volt, one redox couple. Similarly, the negative side also some minus 1.5 volt, you have some redox couples. So while scanning these two, while scanning the cyclic voltammetry, these two extreme ends, so you can able to see the current. It is like called ECL current. Okay, so this is happens because you cannot expect that all redox couples can generate the ECL. Okay, so this thermodynamics will tells the energetic electron transfer where it happens. There only you can see the ECL emissions. So this enthalpy change, we know that the formula delta H is equal to delta G T delta S. So the delta G you can is nothing but standard reduction potential of donor acceptor or anionic radical and cationic radical. Okay, this 0.1 EV like entropy factor. So if you put it this, then maximum 2.1 volt you may get for this kind of diphenyl anthracene. Then because of this huge potential, you can able to generate the annihilation mechanism. So, this is the reaction mechanism behind the annihilation mechanism, but it has some drawbacks. So, what are the drawbacks? It always needs wider range potential. Wider range potential means, see, you have to scan minus 2 volt to plus 2 volt. Okay, and when you go for minus 2, because there only you can see this diphenyl anthracene or similar molecules source these redox couples and generate the intermediates. So once if you go this kind of wider potential window, ultimately you cannot use aqueous solvents. So you have to, because aqueous solvents always generate HER or OER. Okay, it depends upon which direction you are scanning that. It always limits the kinetics of this redox molecule. Okay, so mostly you have to use non-aqueous solvents, which ultimately it is very tough. Okay, if you go for some biological based biosensor point of view, non-aqueous you obviously cannot use. Okay, so this limits the application of ECL, especially biosensors. So to avoid or to overcome this issue, people come up with some other new mechanism. Is called a co-reactant mechanism. Okay, so this co-reactant mechanism means people are adding additional reagent along with that okay. So, excuse me, please mute that crosstalks are there. So people are using some additional reagents where that additional reagent helps to generate some intermediates which ultimately oxidize or reduce that particular molecule. So this co-reactant has two reaction mechanism. Okay, one is called oxidative reduction mechanism. So that means you no need to go negative potential window. Okay, just you go only one direction. Like unlike annihilation mechanism, you just go one direction from 0 to 1 volt or 1.5 volt. Okay, there if you that same ruthenium or diphenyl anthracene will oxidize maybe 1.1 volt. But when you add a reagent like tripropyl amine, okay, that will oxidize first below that redox molecule. Like you can see here that cyclic voltammetric response of the top is like CV behavior, that below has that ECL response. Okay, that where that dark line, that black color response shows that there is no redox molecule. It's like a background current. Okay, so when you that blue color response shows that ruthenium oxidized at 1.1 volt and give the wonderful redox molecule. But parallelly, these two, the black and the blue, doesn't show any ECL emission. But similarly, when you use that tripropyl amine, which also oxidized before that 1.1 volt, the redox molecule of RuBP. It is like it started around 0.6 volt. Okay, that is the indication of a red color. But still there is no ECL, okay, because there is no luminophore. But when you mix these two, okay, that RuBP and tripropyl amine, when you are mixing into the electrolyte solution of phosphate buffer, then when you are scanning, so you can able to see the ECL signal, like below bottom of that blue color, that the reversible peak becomes irreversible, and you can able to see the light emission. Okay, this blue color bottom of the line, you can see the light emissions current response. Okay, so this is where the greater advantage, you don't need to go for wide and produce this tripropyl anionic radical, cationic radical, which has highly reducing capability. Okay, this intermediate has highly reducing capability after deprotonation. Okay, then when you go for a little bit beyond that that particular potential, ruthenium 2 plus initially oxidation state, it will convert it to 3 plus. Okay, that 3 plus and that TPRA dot radical will interact together and it promotes to ruthenium 2 plus star. It is called excited state. Okay, then once it goes to the excited state, ultimately it decays the light and comes to the ground state. So I hope you all understand the oxidative reduction mechanism. So one molecule will oxidize the reactant. Okay. Similarly, instead of going a positive side, if you go the negative side, okay, so you can also able to generate ECL, okay, in aqueous medium. Okay, that is the typical example I am telling. I am showing here the same ruthenium molecule. When you use persulfate, okay, sulfate will reduce first, okay, around maybe 600 millivolt or 0.6 volt. That persulfate will reduce and produce persulfate anion radical. Okay, after that ruthenium 2 plus will reduce to 1 plus. Okay, that is the cyclic voltammetric response of bottom one. Okay, then when these two, that sulfate anion radical and ruthenium 1 plus will interact together at the interface and promote to the ruthenium 2 plus star. Okay, then ultimately it decays the line. So this is called reductive oxidation mechanism. So the reductive oxidation mechanism means that reducing that persulfate will reduce first and generate anion radical, which highly capability of oxidizing power will reduce, will oxidize that ruthenium 1 plus to promote the ruthenium 2 plus. So this is called reductive oxidation mechanism in co-reactant. So the major advantage, unlike annihilation, it has some narrow potential window. Either one direction we can go, like anode or cathode, which depends upon which kind of additional reagent you are choosing. So some oxidizing molecules if you are using, okay, you can go for anodic side, or if you use some reductive side, you can use some typical co-reactants. Okay, and this co-reactant also applicable in both aqueous and non-aqueous. And especially this most of the biosensors, people always use this co-reactant mechanism because it always works in neutral buffer or in alkaline buffer. Okay, So that is the greatest advantage, and I hope you all know what is the ECL and what kind of reaction mechanism following this ECL. Because once if you understand this, then only you can follow my subsequent slides where we are doing the research towards biosensing or by developing some luminophores. So I am going to give you some brief. So what kind of luminophores people are exploring or developed so far? Okay. So if you look at the luminophores, because all the molecules you cannot use as so some molecules like organic molecule like luminol, polyaromatic hydrocarbons. Okay, these are all the aromatic molecules will act as a luminophore to generate ECL. Okay, similarly organometallic compounds like ruthenium bis tripyridyl or iridium complexes also give a wonderful ECL. Okay, and semiconducting nanostructures. Okay, semiconducting nanostructures are quantum dots or metal clusters, are recently people are using polyconjugated carbon dots. So these are all the materials, particularly nanomaterials, behaves like semiconductors. That semiconductors one can injecting the electron or withdrawing or creating a hole, one can able to promote the excited state of that particular molecule by electrochemical gain. So that I am going to tell you some typical example in my subsequent slides. But normally these are all the few examples of luminophores. Still people are spending their time to develop some new kind of luminophores which has more stable luminescence emissions. Okay, for some particular biosensing applications or LED based devices. Okay. And similarly, anodic co-reactant, as I said, that the co-reactants also, people always, they are also developing co-reactant because which also helps to generate the ECL. Okay, so tripropylamine, dibutyl aminoethanol, oxalate, NADH are kind of some biomolecules will also act as a co-reactant which generate the ECL, especially anodic co-reactants. In cathodic co-reactants, people will use hydrogen peroxide as a primary co-reactant because it always helps. Because normally in biological fluid, O2 has the main source. Okay, that will reduce and produce hydrogen peroxide. So most of the in vivo or in vitro or biosensors, people will use this hydrogen peroxide as a co-reactant by in situ generations. Okay, rather than that persulfate or benzyl peroxide or hydrazine. Okay, the hydrogen peroxide is one of the best co-reactant in cathodic side. Okay, to go for some biosensor applications. But, so still people are paying more attention to develop a novel co-reactants for generating or high intense ECL signal for typical some applications, especially in biosensors. So I am showing a tabular column here that what I mentioned, that oxidative reduction, okay, and reductive oxidation, what kind of luminophores, what kind of intermediates, okay, then what kind of potential that where that exact that intermediate potential for generating the ECLs. But to knowing to understand the concept, so you have to see this kind of statistical literature. Okay. So this is the few information, but ultimately we follow the thermodynamics. Otherwise, we cannot able to see the light emissions. So as I mentioned in my previous slide, so semiconductors are quantum dots. Okay, by scanning the cathodic side, one can able to generate the hole. Okay, in the band gap region, also the conduction band, valency band, and ultimately it recombines. Okay, recombination will take place and emit the lights. Okay, during anodic side. Similarly, cathodic side, one can inject the electron by reduction, okay, and creating a injecting an electron and generating the ECL. Okay, so the same semiconductor, so the same principle like reductive oxidation or oxidative reduction mechanism follows for nanomaterials kind of quantum dots, metal clusters. Okay, by recombination mechanisms. Okay. See, this is another typical example. Recently, people developed some gold metal clusters, especially AU25 behaves like a molecule. Okay, when you use triethylamine as a co-reactant, these two, the cyclic voltammetric response I am showing the right side. Okay, when you put these two, will oxidize that, and you can see the left side. You can see the light emission. Okay. So this metal clusters also behaves like a molecule and generate the ECL, and because of more advantage. These metal clusters are bio-friendly and it can be used in biosensor applications. So, as I mentioned my initial slides, since this is like assemble technique. There is no commercial instrument so far. Some of the labs, so those who are all worked with Professor Bond, like pioneer worker, they developed this technique, and those who got the training, they are inbuilding in their own labs and performing or doing their ACL based research. So, as I mentioned, no, that this ECL, homemade ECL or indigenous ECL doesn't involve too many components. Okay, so the same potentiostat, same electrochemical cells. Only thing you need a PMT. It is called. It is like heart of ECL. You can say it is PMT is like a photo multiplier tube. Okay, if when you during that electrochemical reaction, when you put that PMT in the bottom of the electrochemical cell, so it receives the, if that light emission occurs on the electrode surface, that photomultiplier tube is more sensitive to the capturing of lights. Okay, so that will receive the signals, and that signals always very less. Okay, so that that should be amplified. Oh, that you need some high voltage amplifier. Ultimately, this electrometer helps to read out the technology. Okay, so these are all the components we need to inbuild the homemade ECL setup. So so now you know what is ECL, what is the mechanism, how that homemade ECL assembly happens. Okay, on some developing a novel co-reactant where you can use for some biosensor applications. As I mentioned, the hydrogen peroxide is a well-known co-reactant for cathodic ECL. Okay, since that dissolved oxygen itself electrochemically generate the dissolved oxygen to produce OH radicals or the hydrogen peroxide reduction. Okay. So we have identified glutathione is one of the biomolecule which also behaves like co-reactant, because you know, all of you know, glutathione is a common non-protein diol molecule present in living cell. Okay, which has the tripeptide linkage consistence of glutamine, cysteine, and glycine as the amino acids linkage. So it is like important endogenous antioxidant and play a crucial role in biological system towards detoxification of variety of electrophilic compounds and peroxidase. Okay, so these are all. So this is the more the importance of glutathione. So we identified glutathione as a co-reactant. Once if you know the co-reactant, it ultimately generates the ECL. So by generating the ECL, one can able to sense or how much glutathione present on the biological body. So also you know the glutathione always exists in the reduced form and oxidized form. The reduced form means only one GS glutathione radical. Oxidized form means coupling of these two, one GS molecule by it is like a dimer of oxidation glutathione. Go for electrochemical method, you cannot distinguish which one is the reduced form, which one is the oxidized form. Okay, but so the glutathione molecule. So the anomalous level of GSH or the ratio of oxidation at reduced form may cause health conditions like Alzheimer's diseases, Parkinson's. Okay, so it always, so this tells that it needs some biosensor. Okay, for to identify or estimate the glutathione. For that we are using ECL technique. Okay, there we identified glutathione as a co-reactant. How we find that glutathione will act as a co-reactant? So here you can see like cyclic voltammetry. So we have that facility. One can simultaneously we can record cyclic voltammetry as well as ECL signals. Okay, so this is the cyclic voltammetry shows the CV and ECL response. When you look at that A response, it is like we are here using ruthenium tristriperyl complex as a luminophore. So it shows a typical redox response at minus 1.5 volt. Okay, but if alone there is no ECL, that is where I am showing some the kind of response in B. okay, glutathione, then you can see how much that green color shows the enhanced ECL. Okay, but there is no typical, there is not that much appreciable change in CV, but you can see the ECL changes. Okay, that green color shows when you add ruthenium in glutathione reduced form, you can able to see the ECL emission. Okay, then when you use, so we thought that maybe the signal is very, very less. Okay, but how we can improve that? Because we know that always this OH ions always quench the ECL reactions. So we deaerated that buffer solutions by passing or purging a nitrogen gas. Obviously, the red color. So after deaeration, you can see a clear, well-defined redox peaks in CV, and there is no peak on this redox chemistry. Okay, but well-known the cathodic ECL, it is shown in the red color. So this deaeration helps to improve the ECL signal, and we are eliminating the oxygen reduction peak. Okay. So to confirm this real that OH ions are influencing the GC, when we add that radical reagent into that similar solution, ultimately there is no ECL. Okay, that is the D indication. So this tells that even though we are deaerating the oxygen, but still you need a small trace of oxygen molecule that will produce OH radical that will help to to generate the GS radical, and this GS radical will interact with the RuBP and produce the ECL signal. Okay, so this is the one we have believed initially by putting the deaeration and sodium sulfate. We are confirming that you need a small OH radical. So the same experiments we are performing with glutathione, the oxidation form of glutathione. So that means here there is no like protonation, only a dimer of that glutathione molecule. Here it is like independent. Okay, even there is no, it is like independent means when you are deaerating the buffer solution, you can able to see a very good ECL signals like red color. Okay, that means each molecule produce 2 GS radical. So that is where the intensity of ECL signals are very high when compared with the reduced form. And when you add any sodium sulfate, it doesn't involve this, it doesn't involve, or there is no passivation of ECL signal. When you add even sodium sulfate, that means, but ultimately GS-SG radical will break and produce GS radical. And ECL response, we are proposing a reaction mechanism. Like the reduced form depends on a small OH ions or OH radicals that will produce GS radical. That GS radical ultimately interact with the that ruthenium 2 plus, that ruthenium 2 plus, ruthenium 2 plus to 1 plus, then 1 plus and GS radical promote the excited state of RuBP molecule. But in the case of oxidized form, okay, this oxidized form, there is no need of OH radical. So when you go for negative direction, or that that bulk ruthenium 2 plus will interact with the GS-SG and produce the GS radical. That GS radical ultimately it interacts, and that signals always it is doubled because the reduced form has 2 GS radical. So we have to confirm whether the light emission is happening because of this ruthenium or not. So for that we need to record the spectra that is called ECL spectra. Even we can compare this spectra with the normal fluorescence spectra. So normally fluorescence spectra, ruthenium gives almost 610 redox, that 610 nanometer wavelength signals. Okay. Similarly, our ECL spectra also, when we recorded in situ, you can able to see the intensity that wavelength emission at 650. So this is like it is confirming. It is like a consistency with the PL emission, and the intensity of ECL signal is very high when you use oxidation form because 2 GS radical always generating. And if you look at the stability, like IT experiments when we are performing, So almost 140 seconds, there is no decay in ECL signal. Okay. So based on that, when you change the concentration of glutathione, okay, so you can able to see the intensity changes of ECL signal. Intensity of ECL signals. Okay, based on that, we can put a calibration plot and what we can know. We can able to see the unknown concentration of glutathione using this calibration plot. So this is the one we started with. So I can say because of this work, we can say what can able to sense the glutathione using a novel co-reactant mechanism. Okay, similarly, we have developed another co-reactant like animated or aminated carbon quantum dots as a co-reactant, which specifically quench or sense the butane reductions. Okay, so this is like anodic co-reactant. So because of this amine group will oxidize, okay, and this functionalized carbon quantum dots specifically interact with the butane. So mechanism. So when you use animated CQD, it will source a very good high ECL intensity. Okay, it follows the oxidative reduction mechanism, and you see if that depends upon the electrode surface. Also, we can able to see the ECL intensity changes, and using this aminated carbon quantum dots, one can able to sense or selectively quench the butene molecule, which is biologically more important biomolecule. Okay. So this works also one of the important work in biosensing applications. Similarly, we have developed a phosphorus doped carbon quantum dots, which has okay, that is similar kind of. So we have developed phosphorus doped quantum dots as okay, and shows a very good platform for selective sensing of copper 2 ion. Copper 2 ions, also more important when the abnormal concentration level it disorder like Alzheimer's, Parkinson's, or Wilson diseases. So it is very challenging to estimate this copper 2 plus ions. So even this kind of metal ions, people always use stripping voltammetry, but stripping limitations to avoid the limitations, people are utilizing the ECL based technique by they developed a phosphorus doped CDQ. By the chemistry behind or the novelty of behind this copper ion sensing like a Fenton chemistry. So people will know that iron going to be as a good catalyst for generating OH radical when it interacts with the hydrogen peroxide. So the similar chemistry, when we use copper 2 plus in hydrogen peroxide, okay, when you use hydrogen peroxide as a reductant, then in the presence of Cu2 plus, it generates more OH ions. So based on that Cu2 plus concentration, the generation of OH radicals are very high, and ultimately we are indirectly estimating the copper 2 plus ion. So these are the schematic diagram we have shown. The phosphorus doped carbon quantum dots platform produce less OH radical with when there is no hydrogen peroxide. Okay, but when you use hydrogen peroxide along with Cu2 plus, it generates more. It is like ECL on mechanism. So normally this kind of metal ion sensing always goes as a quenching mechanism, but first time we are showing some on mechanism. On mechanism has always more advantage. So this Cu2 plus generate more OH ions, which ultimately tells the unknown concentration of or unknown concentration of Cu plus by calibrating or by the calibration plot, and it doesn't have any other interference. Like if you look at a similar kind of other metal like sodium, magnesium, aluminum, and all, because these are all the molecules are very inactive, or there is no that much interactions are with the hydrogen peroxide produce OH radical. So it shows selective for copper 2 plus ion sensing. And also we have compared the some other known co-reactants, okay, and sensitivity point of view, we have compared the literature, and this whatever the sensitivity we achieved, it should be comparable with reported literature values. And recently we have come up with another one more novel co-reactant. For that we used luminol. Luminol, as I said, it is like organic luminophore. The dicyclohexylamine, we have used dicyclohexylamine as a co-reactant, okay, which is honey adulterant. Okay, one of the in commercial market so many honeys are there, but ultimately people will use this kind of molecule as an adulterant to estimate or to sense the DCH. We identified this DCH molecule as a co-reactant, and we successfully demonstrated by using a flow injection analysis. It is like a flow injection analysis means it is like a similar real situation. Okay, so we demonstrated and source the maybe some picomolar or nanomolar sensitivity of DCH. Okay. So apart from this, if you see the literature, people still like we have developed novel co-reactants, novel luminophores. Now people are going with instead of putting two molecules like a luminophore co-reactant, people are developing a 2-in-1 molecule. Like means that luminophore has by tethering chemistry or functionalization chemistry, people are functionalizing the co-reactant molecule into that luminophore. Okay, so it is like amine-rich nitrogen doped carbon quantum dots they are developing, which has both. Okay, so that means it eliminates the intermolecular interactions. Maybe the sensitivity going to be or intensity of the ECL going to be very high. Okay, so this is one kind of research people are identifying or developing the 2-in-1 molecule rather than individual co-reactant or novel luminophore. Similarly, people are also identifying like in situ generated co-reactants like BPD electrode. When you reduce or oxidize to produce the SO4 minus radical, sulfate anion radical. Once you have that sulfate anion radical, ultimately it interacts with the ECL. So this is also like it eliminates the additional reagents. When you go for biological systems, okay, so this kind of in situ reagents are more important.
Hello, sir. No help. Was sir, no file purchase DSC. Sir, first select tick
sir. Okay, so apart from these two, identifying some novel luminophores or co-reactants, people are now utilizing this ECL technique for fingerprint sensing. Okay, by putting a smart cameras. Okay, see, normally it is now useful for bioplant or implantable sensors because you don't need to depend on potentiostat and all. Okay, so that by capturing a light, okay, that photo, we can able to see the image by triggering, because this smartphone has that software or okay, some software one can able to trigger that IT curves. Okay, based on that IT curve, you can able to trigger the electrochemical reactions, and putting that camera you can use as here like a PMT. Okay, that capture the image, and when you the fingerprint regions I am showing here, when the nicotine or some drugs people are touching in their hand, so when you place your camera front that one, and you have that inbuilt IT curves. Okay, one can able to detect who is having that nicotine in their hands. Okay, so this kind of ECL imaging people are developing. Okay, so now the trend is little bit because normally that smart cameras has some sensitivity issue. So for that, people are using CCD cameras, which has more sensitive, which have the capability of analyzing single cell reductions. Okay, so overall, I can say my conclusion: ECL is a unique kind of technique which where you can able to go for some biosensing applications. So you have a lot of hopes in doing science by identifying or developing a novel co-reactants like aggregation-induced ECl, polymer quantum dots, and some other composite molecules, metal organic framework or metal clusters, luminol derivatives. These are all where you can go for developing a luminophores or co-reactants, and ultimately you can use for like biosensor, DNA, cells, imaging, metal ion sensing, small molecules, proteins, etc. Okay. So thank you, and I can so Sir Alan J. Bard, University of Texas, who host me for supporting my fellowship and allow me to learn this kind of ECL technique. Okay, without him, definitely I cannot able to inbuild in my lab. So after coming back 1 year's time, I have inbuilt my own with the help of funding agency like BST, CSIR, and my own group. Like my students are continuously pursuing the PhD work and developing a novel luminophores or co-reactants for some biosensor applications. Thank you for your kind attention. I am very happy to answer you some questions.
Thank you, Professor, for your wonderful presentation. So the audience, please the session is open for discussion. Please, the participant can clarify their questions.
Thank you, sir. Sir, thank you very much for your interesting lecture. I am Vasanta, sir.
Thanks,
sir. Really, sitting is a great place for me. And you, without you people, this event also would not be arranged smoothly. So you supported me.
Thank you so much, madam.
Sir, is it now audible, sir?
Yeah.
Sorry, sir. Sir, actually, I have small doubt.
Okay.
The detection of copper, you showed some slide about the detection of copper, sir.
Yeah.
Sir, actually, for detection of copper, stripping voltammetry, as you said, stripping voltammetry is a best technique, but ECL is a costly technique.
No, madam. It is like not. I am saying, it is not a costly technique. If you have some typical PMT or even smart camera is sufficient nowadays. Okay, with the handheld potentiometer. But as you said, that stripping voltammetry, when you go for some selectivity, you cannot expect, correct? But here, the identifying the reaction mechanism, or how we designed the chemistry, okay, the Fenton chemistry we are utilizing to go for selective detection. So that is the merit.
For some special application. This is for some. It
cannot
be used. The stripping cannot voltammetry cannot be used in that place. No, sir.
Yeah. Because stripping means always is like other molecules also will show signals.
Yeah.
Okay, but there is no control, correct? Except the potential holding. In the real situation, you cannot expect. But here, whatever we have developed, that chemistry, it is like Fenton chemistry.
Yeah.
That is more important in choosing the selectivity. We are not doing like no real sample analysis because we don't have such a facility. But using this concept.
Okay. Sir, actually, even immunoassay can be developed in ECL. Using
yeah, of course. See, lot of I can say because I am not showing because I saw Nuts slide. He is going to talk immuno. So that is where I did not show. But nowadays, 180, I think. Literature says that 180 immunoassays are there for commercial basis. In clinical commercial tests, people are using in their healthcare applications.
Sir, what is the real application, industrial application of ECL, sir?
Yeah, it is like, especially that's what I am telling you, that the antibody antigen interactions and all. So that's using some square wave algorithm. Okay, but here there is no algorithm to sense that antibody antigen.
Even nowadays, name of the industries. I am asking name of the industry. Which industry?
Industry means that whoever is developing healthcare devices like Roche or some other, maybe Roche is a pioneer worker developing more than 100 assays is based on ECL. It is like ELISA. It is a complementary technique for ELISA.
Yeah, ELISA.
Yes.
But it may be a highly sensitive, no?
Yeah, it is highly sensitive.
Compared to ELISA.
Yes. because you have coupling two techniques. So the electrochemistry and optical. So it overcomes the individual limitations. And there is no background signal. Like when you go for electrochemistry, obviously you may see that background signal. It limits the sensitivity.
Non-Faraday current is completely eliminated.
Yeah, because there is nothing here. Only we are observing the light emission. Even if you use a bigger size electrode, you don't need to worry about anything.
Okay. Electrode area, it doesn't play any role here.
Yes.
Thank you, sir. Thank you for all your support for this
Thanks, madam.
conference.
Any other questions from audience?
Madam, one comment, Professor.
Tell me, sir.
Professor has several projects with several crores, so that that ECL may not be costly for him. Maybe MQE it will be costly.
No, sir. That PMT cost around 2 lakhs. That's all.
Okay.
If you purchase a PMT and you have good electronic person, you can able to inbuilt your own. But only thing, some tricks are there. Okay. That you have to either come to my lab or visit to some pioneer workers like Bard or that is the.
Very few people are working in this field, sir, in India.
Yeah. Even nowadays, Pitts Pilani, one of professor, instead of using this kind of PPT, he is using by capturing, but he may not bother about the kinetics or mechanism, action mechanism. But ultimately, putting a luminophore and a particular biomolecule, okay, he can able to image by putting a smart camera. Yes, I said that fingerprint regions and all. No, so for that even you can replace with the PMT.
Okay. It's a very simple model.
Yes. It is very simple model, but only thing the understanding of the luminophore chemistry is more important.
And handling the technique is very
easy. Even we are now developing a portable ECL based one. Okay, almost we are in the middle of that one. Maybe if that is success, maybe even I can take to field work.
Okay. Thank you, sir.
Participants, is there any questions? So, in the absence of the further questions, I thank Professor Dr. Sendil Kumar for his wonderful lecture. And he has started from the basic fundamental of electrochemistry, ECL, to the recent applications. So he is very proud to say thanks to thank for his wonderful lecture. And I also
thank you so much, sir. Wholeheartedly, we thank for your wonderful and colorful electrochemical excitation for an hour. It's really fantabulous to keenly observe each slide to the participant as well as to me. And personally, we would like to thank for being a part in our EDAS family 2022. So on behalf of the organizing team, as well as for ma'am, I would like to thank once again for being a part with us today and also for your wonderful lecture. So in this junction, on behalf of the organizing team, ITARS 2022, I feel personally happy to acknowledge our own Professor, Dr. J. Anaraj sir, Head and Assistant Professor, Department of Material Science, School of Chemistry, Madurai Kamaraj University, to actively lead this platform for the past 1 hour with his noteworthy words. Thank you so much, sir.
Thank you, Raja. Thank you.
Yes, sir. So it's a kind announcement to the participant. And today technical session is now over here. And now it's a time for a lunch break. So we will have a parallel oral and poster session. The link which has been already sent to your registered email, we hope. So we will meet you shortly by 2 p.m. after lunch. The participants who are also being wished to participate in the oral or poster, we are pasting the link in the chat box. If you wish, you can join through oral or poster in the respective link in the chat box. So with this, I thank you once again to all the participants, keynote speaker, chairpersons, and the convener of this program, Vasanta ma'am. Now I conclude this session. Yes, ma'am.
And the problem is justified, so I was asked them to inform to their friends.
Yes. So it's a kind announcement and sincere apologies. We have actually borrow for more than 300 participants in the Zoom, but due to some technical issues, it can't accept all the 300 participants. Now the problem is rectified, and we hope tomorrow it won't be exist. So tomorrow we have two wonderful sessions along with one instrumental demo also. So I request all the participants that don't miss, and I personally request kindly mute your audio and video during the session, because we bring all those wonderful personalities from all over the world to you through this virtual meet, and it's personally disturbed to them as well as us. So it's a kind request once again, and we are expecting your full cooperation and attendance for tomorrow also. Tomorrow we have a technical session 2 with the two wonderful personalities, Alan Valgaris and Mamas. So both two persons are really a wonderful agenda they have in various editorial platforms. So with this, I thank you once again, and we will meet you in the afternoon session. That means oral and poster in through Gmeet. So I request all the oral and poster participants get ready after your lunch, and we will meet you shortly again on 2 p.m. Thank you so much. Now you can left from this platform, and the oral poster Gmeet link is pasted in the chat box. Those who are willing, you can join through this link. Thank you so much.
Sir, the only good பண்ணிட்டேன் sir. Sir, இவரை நான்